In the last few lectures we saw how to use the Gelfand-Mark theorem to develop what is known as continuous functional calculus. That means for each continuous function we had an operator which was the inverse Gelfand transform, right. And using that we define these measures mu u comma v and extended this continuous functional calculus to bounded functions, right, which we call L infinity functional calculus. Once we reach L infinity functional calculus, you can take for bounded functions you can take chi e, that is indicator of Borel set E or characteristic function of E, and we got projections as the image, right. So, we call that P of E, and E, the set E going to the projection P of E had certain properties, right. It was additive and there was a countable additivity in the strong operator topology and so on. Okay. So, now what we do is we sort of go in the opposite direction, in the sense that we start with this projection valued map, which we will call a projection valued measure, and then try to develop the L infinity functional calculus, and we will see that these two are essentially equivalent. Okay. So, let us start. So, we saw that if I have a Hilbert space, a projection valued measure is, so that is what we call the map P from the sigma algebra F. So, the omega could be some set. Okay. So, in the concrete case it is going to be the spectrum and F is going to be the Borel sigma algebra, but here it is a abstract setting, and a map P. So, we will denote it by P, a projection valued measure, if first of all each E gives me an orthogonal projection, right. So, that means P E equal to P E star equal to P E square, and of course, the empty set should go to 0 and the whole set should go to identity, which is like a probability measure if you like, and it has this property that P intersection F equal to P E times P F. In other words, if E and F are disjoint, then the product is 0. So, that is reminiscent of whatever you saw in the finite dimensional case, where if you have distinct eigenvalues, the corresponding eigenspaces are orthogonal to each other, right. And the last one is the convergence in the strong operator topology, which is essentially countable additivity. Such an object is called a projection valued measure. Okay. So, we continue from here. So, it follows that if I take u and v in Hilbert space H, we are going to construct that measure mu u v. Of course, we will denote it by P, P u v of E equal to P E. So, P E is a projection, acting on u is a vector, inner product with another vector v, right. So, that is a complex number. So, this is a complex measure, is a complex measure. So, you have to check the countable additivity, right. So, let us do that. So, suppose E j are disjoint. Okay. So, j equal to 1 to infinity. So, let us write that as well. So, j equal to 1 to infinity is disjoint. Then I want to know what happens to P u v of E j, right. So, P u v of E j or union E j, right. So, j let us let us take finite union. First of all, j equal to 1 to n E j P union E j. So, if I look at u inner product with v, so this is of course going to be, because of whatever we have here, the finite sum will give me summation, this is equal to j equal to 1 to n P E j u v, right. If you have countable additivity, you have finite additivity, right. So, So, this is a trivial thing, you can take all the Ej's to be empty set for j larger than n and you will get this, right, and this will converge to summation j equal to 1 to infinity p e j u v, right, because of the strong operator topology. So, we have the sum j equal to 1 to n p e j u converging to sum j equal to 1 to infinity p e j u, right. And so, this check that. So, the thing to check is that this is actually an absolute convergence. So, check that summation j equal to 1 to infinity p e j u v converges absolutely. Okay, this is important, right, because otherwise you do not have a complex measure. You want the convergence to be absolute convergence. So, that if you change the order of the Ej's, nothing much is changing. Okay. So, that follows from the fact that you have strong operator topology convergence. Okay. And remember that PEJs are projections, and if EJs are disjoint, then their ranges are also orthogonal to each other. So, PEJU and PEKU are orthogonal to each other. So, when you take the norm, you are simply adding the norm sum square, okay, and so from that it will follow that this summation converges absolutely. Okay. So, it is a complex measure, and note that when u equal to v, it becomes a positive measure, right. So, p u is a positive measure. So, it is a positive finite measure, right, finite measure. Okay. And the norm of p u u, so that is the total variation norm, but this is a positive measure. So, this is simply p u u of the whole space, right, and that is p u sorry omega u acting on u, but that is identity, right, p omega is identity. So, you have norm u square. Okay. So, keep that in mind because we will be using that. All right. So, let us continue, but before that let us look at a easy example. So, take omega to be closed interval 0 1 or any other set in the real line or complex plane, it will work exactly the same way. Okay. So, script f is the Borel sigma algebra of 0 1, okay, and take Hilbert space to be L2 of that space, L2 of 0 1, okay. And now for each E in F, so I should give you PE, right. So, PE is going to be a projection on H, right. So, PE is an orthogonal projection from H to H, right. So, how is it defined? So, I am going to define PE of, well, H is L2 of 0 1. So, I take some function f, and then I should tell you what is the result, that is chi e times f, right. So, that is a, so it is just multiplication by chi e, right, and then chi e. So, if I have a multiplication operator, so if I multiply by phi, then its adjoint is multiplication by phi bar, right, and the square of that operator is multiplication by phi square, right. So, the fact that chi e equal to chi e bar equal to chi e square implies P e equal to P e star, right. The adjoint of P e will be multiplication by chi e bar, but that is chi e equal to P e square, right. P e square is multiplication by chi e 2 times, but chi e times chi e is chi e itself, right. So, this tells me that each P e is an orthogonal projection, right. So, that is a projection valued measure, and we have seen what how the measure P u u will look like, right. P u v, it would be measure given by the function u times v bar, right. Okay. So, one more definition here before we go further. Definition: if omega is a locally compact T2 space, okay, and script f is the Borel sigma algebra, Borel sigma algebra of omega, then a projection valued measure P. So, this will go from script f to bounded operators on H, and for each set E we have a projection, right, is called regular if P u v. So, remember these measures we just defined, right, for each u and v we can define the measure P u v, right. So, this is how it is defined. This measure, so that is a complex measure on a locally compact Hausdorff space, so is regular. So, this makes sense, right, because now you have open sets, closed sets and so on. Okay. So, okay. All right. So, the projection valued measure is called regular if these measures are regular. Okay. So, now what we are going to do is we are going to start with the projection valued measure and then go in the opposite direction, in the sense that define L infinity functional calculus. Now, the L infinity functional calculus we obtained was for any function, any bounded function, we had an operator, and that assignment, that bounded function going to an operator was a star algebra homomorphism, right, which was continuous and so on. So, if I take f and g, then f g should go to the corresponding product of operators, f bar should go to the adjoint and things like that. Okay. So, we are going to develop that, and that is essentially integration against this projection valued measure P. Now, when you do the usual integration, you know how it is done. You start with a measure, then you define the integral of simple functions and take limits. Okay. So, you can do the same thing here, but because we have defined these measures P u v's, we can do this directly. Okay. So, it is an equivalent way of doing it. You can start with simple functions, define the integral of the simple function against your projection valued measure and get an operator. We do not get a number like the usual measure theory, we get an operator and see how to take limits. Okay. But we will do this directly by integrating. Okay. So, next we define integration against a projection valued measure, So, PVM stands for projection valued measure. Okay. So, let B omega be the, so there is no script B will stand for Borel sigma algebra. If it is the usual B, then it is the space of bounded function, be the space of bounded measurable functions. So, measurable functions because there is a sigma algebra, right. So, that is with respect to a sigma algebra script f which is already given to us, right, where P, the projection valued measure, is defined. So, let B omega be the space of bounded measurable functions on omega. Okay. So, if f belongs to B omega, which means it is a bounded function, we are going to define an operator. Now, if you go back to what we did in the case of L infinity functional calculus and so on, we defined a linear form which was continuous, and that gave us an operator, right. That is precisely what we are going to do. So, if f is in B u and u is in H, consider integral over omega f d p u u. So, remember P u u is a positive measure whose total measure of omega is simply norm u square, right, and f is a bounded function, measurable function, everything is finite. So, this integral makes perfect sense. Okay. So, modulus of this is less than or equal to, of course, I can take the supremum norm of f, outside, and what remains is PUU of omega, right. So, PUU of omega, right, but that we know is norm square. So, L infinity norm times norm u square. Okay. Now, we polarize. So, polarize this. So, we can polarize this because there is some sesquilinear form lurking behind, and polarization is exactly what you have seen in functional analysis. If I give you the norm on a Hilbert space, there is a way to write down the inner product using the norm, right. So, that is you look at the inner product of x and y, you can write it in terms of norm square of x plus y, x minus y, x plus iy and x minus iy, right. So, I will not write down the, I do not remember the exact formula. So, it is norm. So, you can write down the inner product in terms of norm x plus y square, norm x minus y square, norm, since you are on the complex Hilbert space, norm x plus y square, norm x minus y square, right. So, using this you can write down the inner product of x y, right. That is what you mean by polarization. So, here we have the situation similar, we have norm u square here and there is u and u here, right. So, I want to bring in u v there. Now, how do I bring in u v? So, remember the map u comma v going to p u v, the measure is like an inner product, right. It is a sesquilinear form. So, let us we can polarize, because if I look at p u v of E equal to P E, which is my projection acting on U inner product with V, right. So, you can see it is linear in U, antilinear in V, and so it is a sesquilinear form, right, which takes values in measures, right, sorry, projections or measures or complex measures here in this case. And so, one can do the polarization just like you will do for the inner product. Okay. That is what you are. So, essentially I am asking you to write. So, write down P u v, okay, in terms of. So, P u v think of as inner product of u and v, right. Only thing is it is taking values in the complex measures. So, in terms of, well, if you look at the polarization formula, that you should be writing this in terms of u plus v, u minus u plus v, okay, that is u, that is of the form p u u, right, that is a positive measure. Similarly, p u minus v, u minus v, that is also a positive measure, and then p u plus I v, u plus I v, and p u minus I v and u minus I v. Okay. So, bring everything to diagonal kind of elements, right. So, all in terms of p u u. Okay. Well, what will you do? So, you will get from here, you will get we get integral over omega f d p u v. Okay. This would be less than or equal to 1 by 4 times, because you know the inner product of x comma y is written as 1 by 4 times the sum of all the other things, right. Well, there is a norm of L infinity norm coming out, and then I will have u plus v square, because that is p u plus v u plus v, and plus norm u minus v square plus norm u minus I v square plus norm u plus I v square. Okay. Okay, so, we will also assume that norm u equal to norm v equal to 1. So, that is how the polarization would look like, and since norm u equal to norm v equal to 1, we get integral over omega f d p u v is less than or equal to. So, here I have u and v less norm 1. So, when I sum I will get so that is less than or equal to 2 square, that is 4, and here I have 4, here I have another 4, and here I have another 4. So, that is 16 by 4. So, I will get a 4 times the L infinity norm of f, right, at least for u v equal to 1. Now, also remember that the definition of p u v was p e, the projection acting on u inner product with v, right. So, if u and v are not norm 1, you can divide by norm u and norm v, and you see that they come out, right. So, there is homogeneity. So, this is for norm u equal to norm v equal to 1, and so in general integral over omega f d p u v will be less than or equal to 4 times L infinity norm of f, and you will have a norm u times norm v coming out, right. So, look at this, you will see that p u v you can write in terms of norm, you can divide by norm u and norm v and multiply by that, right. So, there is homogeneity there and you will get this. Okay. This 4 is superfluous, this will disappear. Okay. So, we will see this later, this will disappear. So, if you remember the L infinity functional calculus, there was no 4 there, right, and we will see that it disappears at a later stage. Okay. So, right now we are only developing the integration. So, what we have done is, starting with a bounded function, we have just looked at this this one, and which is a sesquilinear form, and it is bounded, right, with 4 times L infinity norm of. Okay. So, let me write down that. Hence, if I look at u comma v going to integral over omega f d p u v, this is a continuous sesquilinear form, right, sesquilinear form. And so, and whenever you have a bilinear form or sesquilinear form of this kind which is bounded, there is an operator, right. So, there exists bounded operator which will depend on f, right. So, let us call it T sub f, we will change that notation soon, T sub f, such that integral over omega f d p u v equal to T sub f acting on u v. Okay. Now, this T sub f is what we want to interpret as integral of f against p. Okay. So, T f is the integral of f with respect to the projection valued measure p, not the usual measure, projection valued measure, and so we will denote it by, we will denote T f by, it is the integral of f with respect to the measure p. Okay. So, remember that this is a operator. Okay. So, integral over omega f d p is an operator. Okay. So, the defining form for that is, if I look at integral over omega f d p, this is an operator, this operator acting on u. So, this is my T sub f, right. So, this operator acting on u, inner product with v is equal to integral over omega f d p u v. Okay. So, this d p u v, you see that is same as mu u v we have defined earlier, right. Only thing is, there we started with a commutative C-star algebra with identity which was contained in the space of operators, and we use the Gelfand transform to define these measures, right. Okay. We are going the other way, as I kept saying. Okay. So, clearly f going to integral over omega f d p is linear, right, because if I change f to f plus g on the right hand side in this defining equation, you see that that splits, and that will give me integral of omega f plus g d p is integral f plus integral g. Okay. So, it is linear. Now, just to sort of justify why this notation is used, integral over omega f d p, let us see what happens when f is a simple function. Okay. So, suppose f is a simple function. Okay. So, let us write this as f equal to summation j equal to 1 to n C j chi e j. right. You can assume Ej to be disjoint and all that, but we may not need that. So, I want to find out, so what is integral over omega f dp, right. So, in the usual measure theory, if you have a simple function, the integral is summation j equal to 1 C j times the measure of Ej's, right, those sets. But here we have a projection valued measure, the measure of Ej's will be P Ej, right, which is a projection, and that should be our operator summation j equal to 1 to n Cj P Ej. So, let us see why this is true. Well, we use the defining equation. So, the defining equation is here. So, I look at, so I want to compute the right hand side and see how it looks like, right. I want to write it as an operator acting on u inner product with v. Okay. So, look at integral over omega f dp uv, right. So, that is well defined. So, this is simply integral over omega f is summation j equal to 1 to n Cj chi ej and dpuv, right. Puv is a complex measure, remember that. So, this is simply integral summation goes outside j equal to 1 to n integral over omega Cj chi ej dpuv, right. So, this is a measure and I am integrating an indicator function. So, I will simply get the measure of that set, right. So, summation j equal to 1 to n Cj P Ej u v, right. P is a projection acting on u inner product with v, right. That is how that P u v is defined, right. Okay. So, now it looks all that you know that it looks familiar. So, this is simply you take the summation C j inside. So, this is summation j equal to 1 to n C j P E j, right. So, I look at inner so maybe let me write this a bit more clearly. This is equal to, so I take the summation out inside. So, I does j equal to 1 to n C j P E j. So, that is an operator, right. That operator acting on u inner product with v, right. So, that is what this is. So, I started with integral of f inner product against this complex measure dp uv, and that by definition is integral over omega f dp, which is my operator acting on u inner product with v, right. That is how it is defined. So, these two operators should be same, which is what we were expecting, right. If f is a simple function, you want integral f d to be exactly this, right. So, hence integral over omega f dp is equal to summation j equal to 1 to n Cj Pej, right, the sum of these projections, right. So, that in fact one could have started from here, define the integral for the simple functions and then take limit, as we generally do in integration theory, right. You define the integral of simple functions first and then you take the integral. One could do it directly because one could define these complex measures PUVs. Okay. So, it became easier, okay, but it agrees with whatever one would have done in the usual sense. Okay. Now, not just this, so also if f is a bounded function, okay, so bounded measurable function. So, remember that when I put a script b there, it becomes the Borel sigma algebra, otherwise it is the space of bounded measurable function. Then since it is bounded, I can choose simple functions which converges uniformly to f, right. So, then there exists fn simple such that fn converges to f uniformly, right, such that norm of fn minus f L infinity norm goes to 0, right, because it is a bounded measurable function. That is one of the elementary things you learn in measure theory. Hence, the if I look at the norm of f dp minus integral fn dp, this is the operator norm, right. So, this operator norm, so okay, I can write this as integral of f minus fn dp, because it is linear and all that, right. And we saw that this is less than or equal to 4 times, right. Remember, there was a 4 which will disappear later, 4 times the L infinity norm of the function you are integrating, and this goes to 0, right. So, the convergence of fn dp on 2 integral over f dp is actually in the operator now, okay. And so integral of f is obtained as the limit of certain Riemann sums, right. So, you can think of these kind of expressions as Riemann sums, right. That is what you do in measure theory, except that these things are all projection valued, okay. So, we will stop with stating this theorem, we will prove the theorem in the next class. So, theorem, if P is an H valued, H projection valued measure, that means P is a projection valued measure on some measurable space, right. So, on omega f, the Hilbert space is H and the projections are operators on H, right. Then the map f going to integral over omega f dp, right. So, using P we have defined the integral of f dp, which is an operator, right. So, this is, then the map is a star homomorphism, well, continuous actually, but we will write down the estimate later on, from bounded measurable function into the bounded operators on the Hilbert space H, right. So, these are bounded operators. Okay, I hope the notation is not confusing, because sometimes script B is for the Borel sigma algebra and so on. Okay. So, this is the theorem we will prove. So, let us stop for the time being. What we are trying to do is to start with the projection valued measure and develop the L infinity functional calculus. So, the theorem we just wrote down says that, right. So, any bounded function gives me an operator via integration against the projection valued measure, okay, and that is going to respect everything. So, in the sense that, well, it is clearly linear and f times g will go to the corresponding product of the operators and f bar will go to the adjoint on the other side, right. So, that is what you mean by a star homomorphism. So, if you recall what we did earlier, starting from a commutative C star algebra with identity which is sitting inside, let us say, bounded operators on a Hilbert space, we managed to, from the continuous calculus, we managed to extend it to L infinity functional calculus, and L infinity functional calculus gave us the projection valued measure, right. So, we are going the other way now, we start with the projection valued measure and develop the L infinity functional calculus. So, you see that these two are going to be equivalent. Okay. So, we will stop here.